Alright, there we have it. So like I said, this is Astronomy 154L. My name is Julius Chapman. I have a mailbox in Live Oak in the office area. It's next to the fridge. If you've been in there, you'll see where it is. Live Oak, 11:30. The meeting time, of course, is here at 11. Class is going to start directly at 11. Usually I have like an intro lecture that I'll give, and so I want to get started as quickly as we can. So please try to make it here on time. You know, if you trickle in late a couple of minutes, I'm not going to be too upset, but I'll be locking the door after about an hour because I don't want to get like all the way through the lecture and then we've all started on labs and then someone comes in and I'm just going to keep the door locked at about an hour in. I have an office at 1118 in Live Oak. It's across the hall. It's on the left side if you're coming in. If you're coming in from the library or what, it's on the left side, on the other side of 1127. My office hours are going to be today at 1:30 to 2:30, and by appointment. You can email me if you need to make a special appointment. We'll work something out and we can meet up. So you're going to need the class materials. You're going to need a lab manual, of course, for all the labs. And you'll need a star wheel as well. The lab manual is like $30 at the bookstore, and this is like $2. So, the first couple of labs, I'll bring printouts, but you get the lab manual as soon as you can, because we're going to be needing it. Course description. So, the idea is it's an introduction to the techniques of observational astronomy, including data acquisition and interpretation. We're going to be using things like parallax and trying to determine distances, the star wheel. There's going to be a telescope lab where you guys can all go out during the day and look at some objects in the sky, as long as you don't look at the sun. It'll be quite painful. The course objective. Oh yeah, here we go. IS course is it's independent of the Astro 152 course, the lecture. So you don't need the lecture to take the class. It's highly recommended because you're going to get a lot of information from the lecture that you may not get here. I'm going to have I'm going to have lectures at the start of each class, but there's no guarantee that I'll be able to cover I won't be able to cover all of the lecture material before each lab. So course objective, testing of astronomical hypotheses using data from observations of the moon, planets, sun, stars, and galaxies. This course can be used to satisfy the lab requirement in the general education, natural sciences, as long as you've completed the 152 course, the lecture. So here's our course schedule. We've got our holiday here. The first lab is going to be the size and scale of the universe. I have it right here. So we'll go over that. It's actually extra credit. There's going to be that, and there's another extra credit opportunity that we'll have for today. So today's lab is pretty relaxed, not too bad. We'll start really on the next lab. That'll be our real start, really. So this is the schedule. There's going to be one quiz and the practical exam as well. And there's going to be 12 labs total, with one being a drop. I mean, we have 2A and 2B, but it makes 12 labs. There's going to be one drop lab. So if you miss one, it's not a big deal. So, course requirements and methods of evaluation. No drinks or food items in the lab. I get thirsty, so water bottles are okay. If you got something like a sealed container, that's okay. No alcohol. Don't be bringing in craziness. No food. I don't want like sticky keyboards and stuff like that. We're not using chemicals or anything like that, so there's nothing dangerous in here, but at the same time, we want to keep the lab nice and clean for the next group. So attendance and participation is mandatory. Don't miss any labs. If it's unavoidable and you need to miss the lab, there are other labs that are being taught, the same lab as other astronomy labs, but they're being taught on different days. This is the Friday lab, and it's at 11, so we're at the very end of the week. When it comes to, like, everyone else has already done the first lab, right? So we're at the very end of the week. You'll need to notify me as soon as possible if you know you're going to miss that Friday. Like, I don't want to say Monday, as soon as possible, because if you tell me on Monday, then they have the whole week to make up the lab before Friday, right? You won't be able to make up the lab after Friday, but if you can come in before Friday and work on it, that'd be good. I'll have to ask some of the other TAs if they have room in their class. but the space is very limited. We don't, there's only 46 computers in here and something like that, so space is really limited. Each student's going to conduct his or her own experiment, and each lab must be turned in by their own student, right? Like you have to turn in your own lab. And it's nice to turn in your neighbor's lab, they don't have to walk up here, but I need you all to turn in your own labs. I'm going to sign it with my signature. That shows that I have the lab, and I will grade it. Anything that doesn't have my signature on it will not have a grade. That's how I'll do it. Okay. Each lab is graded on a 10-point basis. I expect to see calculations where calculations are necessary. No, you can't just put answers. You can use the internet to, like, say you need to find the distance from the Earth to the Sun, which we'll need to do today. You can use Google for that. That's easy. It's fine. I'm not expecting anyone to memorize such things. But if you just look up the answer, I need to see direct calculations proving that you've done it and you've gone through it yourself. So don't look up just the answers, unless I make a special exception. So again, the labs will be all turned in at the end of each lab period. When you're done with the lab, you're pretty much free to go. You can go start your weekend. The lab's gonna be turned in at the very end. I'm gonna sign it, and I will return it to you graded next period, so the week after. Anything after that is not going to be accepted. If you need to miss the lab, you have to turn it in before that Friday that the lab is actually being done. Let's see. Yeah, so you must have the answer sheets directly from the lab manual. It's kind of messed up. It's just, you got to tear it out. You get the frills or whatever, but it has to be on the specified lab sheets. I'll accept it if it's on a copied paper, like say, you write it down, like this is the answer for this one. I'll accept that as long as it's really neat. If it's really messy, and it's hard to read, I'm gonna deduct 2 points from it because it's just get the lab manual as soon as you can. I mean, you don't need it for the first couple of weeks, but sooner the better. If you have any questions, please, just come up to me or raise your hand, and I'll be happy to answer any questions. When it comes to the lab work itself, you're going to benefit the most from doing it yourself, going through the calculations and figuring things out. If you need help, don't hesitate to ask me, the people around you. Everyone turns in their own labs, but work with the people around you, try and figure things out. And academic honesty. So we're all adults here. I expect that everyone does their own work, turns in their own work. I don't want any trickery. We have meetings to figure out what's the next trick people are going to try, and I just don't want to have to deal with any of that. It's going to go to the university. The full, punishments are going to be dealt out that way. So no cheating. As we're all adults, we can handle that. The grading criteria. So there's going to be 12 labs, and the lowest one's going to be dropped. So it'll be graded out of 11, and there's going to be 1 quiz and 1 practical. The practical is 15 points. The quiz is going to be 5 points, and each lab is 10 points. And it's graded on a plus-minus scale system. And that's about it for the syllabus. Any questions on the syllabus? Okay. All right, so before we get started on the lab today and the safety guidelines, and before we get started on any of that, I have a intro lecture here. Shouldn't take too long. The first lab is the size scale of the universe. It's important when working in astronomy to get an understanding of the vastness that is the universe. It's quite impressive how utterly vast that the space really goes on for. And it all begins here in our solar system with our star, right? This is our power source, the engine that powers the solar system. A giant fusion factory in the center of our solar system, our star, the sun. Here we have our Earth where we live. and it's right in the habitable zone. So we're not too close to the sun, so it's not too hot, and then we're not too far away from the sun, so it's not too cold. It's just enough to sustain liquid water and be capable of harboring life, which is us. Here are the terrestrial planets. We have Mercury, Venus, Earth, and Mars, and the size scale of those. As you can see, Venus and Earth quite similar in size, whereas Mars is not. It's quite a bit smaller. Beyond that, past the asteroid belt, which lies between the terrestrial planets and here the Jovian planets, we have Jupiter, Saturn, Uranus, and Neptune. These are much, much larger than the terrestrial planets and are giant. They're gas giants. Putting it all in perspective, these are the different planets in our solar system to scale. Here's our star, the Sun, and you have Jupiter and Saturn, our two largest gas giants. And here we have our small, tiny terrestrial planets. In comparison, it's quite mind-boggling. Here's the solar system. You can see the orbits of them and the asteroid belt separating the terrestrial planets and the Jovian planets. Pluto doesn't quite count as a planet. It is the orbit is quite eccentric, and it's not in the same orbital plane. And there have been other objects found larger even than Pluto, beyond Pluto, getting towards the Kuiper Belt objects. So Pluto is classified as a dwarf planet. Here's an image showing the scale of different stars and different planets. We start here at the top of number 1 with Mercury, Mars, Venus, Earth in order from smallest to largest. Then that smallest object here, this is Earth in the next set of scales, going all the way up to Jupiter. Here's Jupiter, that large planet, shrunk down when compared to this one here, this star here, Sirius. These are all stars going up. Here's Sirius, this gigantic star compared to these other stars, and it keeps getting bigger and bigger, and so we get to there, we get Canis Majoris, one of the largest stars that we have observed. Here's another perspective. That's Canis Majoris, that largest star, compared to our sun, which is the largest star. Well, it is the star in our solar system, the largest object in our solar system. That's intense. That's quite the scale. These are planetary nebula. They are the dying remnants of stars ranging from a size of an eighth, 80% of the sun, going on to 8 times the mass of the sun. When they die, they become these beautiful ionized gas clouds, the planetary nebula. Beyond our solar system, we have our solar interstellar neighborhood, where we have the different stars that surround us in our local area. As you can see, here we have Sirius. Can't really see it very well here, but this is Sirius compared to our sun here. This is our solar system. That was that very large star, which is dwarfed in comparison to Canis Majoris. And these stars here in this local interstellar neighborhood are just one small tiny group in our large galaxy, the Milky Way. The amount of stars in here is truly mind-boggling. And beyond that, this is our local galactic group. As you can see here, we have our Milky Way galaxy. It's hard to possibly read. Here's our Milky Way galaxy here in the center. Some of these other objects, like the Large Magellanic Cloud here. This is the nearest galaxy to us, Andromeda. It is another spiral galaxy, and I believe it's actually on a collision course with us in our galaxy, but will be long gone before any of that ever happens. The vastness of space is just too much. But that's our local galactic group. And beyond that is the Virgo supercluster. That's where our local galactic group lies. And these are superclusters, which are all gigantic clusters of groups of galaxies. These are all just clusters of galaxies. Beyond that, we have the local superclusters with the Virgo supercluster in the center. And all of that on that image are all clusters superclusters of galaxies. And that, beyond all of that, makes up the observable universe. Light takes a certain amount of time to reach us, right? It takes a certain amount of time for the light from the star, our sun, to reach us on Earth. And light has a finite speed, 3 times 10 to the 8 meters per second. It's the fastest thing in the universe, and it's the limit, right? So the universe has only been around for 13.5 billion years or what. So that's as far as time has allowed light to reach us, right? The light that is coming from beyond this region, there hasn't been enough time in the universe for it to actually reach us yet. And so that is what this observable universe is. It is the limit at which we can see, and it is expanding every moment as time goes on, and the light further and further away becomes more and more visible to us. Here's another image of the observable universe with our Virgo supercluster in the center there. And here we are back on Earth, looking up at the night sky and our galaxy, the Milky Way. When you look back after seeing all this, it's truly breathtaking, the smallness of our planet. Yes?
What elevation would you have to be to see something?
What elevation? I'm not sure. Light pollution, to see the Milky Way, the light pollution would have to be quite low. I think you could see it, like if you go to the desert, I think you could see it. I don't think you have to necessarily be at a high elevation. It's more about how much light is around you. Yeah. But that's quite a breathtaking image. Yeah, so that about ends the lecture, the intro lecture. Hopefully you've all gained a little bit of perspective on the scale of the universe, because that's what our first lab is going to be about. So I'm going to take our lab here and I'm going to place it on the table over there. Everyone can get up and pick one up. This is going to be our first assignment for the day. So yeah, so we have our lab, we have the safety guidelines, everyone can pick up on that, and we have an extra sheet of paper,
Is there a way to sharpen the image?
There may be a way.
Not that specific one, but just in general.
On the PowerPoint?
Yeah, it's
No, yeah.
I think it's the projector.
Yeah, I think it is the limit on the projector. Yeah. Yeah, I came in here and tested it earlier, and yeah, sorry about that. I can post the lecture on the Moodle, and if you wanna pull it up, you absolutely can. Bless you. So make sure to pick up one of each paper. There's 3 papers there. One's a blank paper. Pick that up as well. It's going to be our second extra credit opportunity for the day. Boom. Okay. So all right. So that's the first data sheet. So you should all have 3 papers now in front of you. The first data sheet for the first lab, a blank piece of paper, and the safety guidelines. Okay, so let's first take a look at the safety guidelines, get that knocked out. So everyone go ahead and sign this. Let's go over it real quick though. So subjects covered, general safety rules. Again, no eating, drinking, smoking in the lab. Smoke-free campus now, but definitely no smoking in the lab. There's no chemicals, like I said earlier, there's no chemicals in the lab, so drinking is okay as long as it's from like bottled water or something that's closable. I don't want any spills in the lab. Just makes a headache for our key master, the lab master Victor. So no unauthorized experiments. I mean, you don't have to worry about that. Don't like sneak off with the telescopes and try and look at stuff like that. I mean, we're gonna have our designated day. So, but let's see. Fine loose, long hair. No, you don't have to do that. No loose clothing. It's all good. That's quite fine. Wash your hands after using chemicals. Again, no chemicals, no problems there. Please do report spills. I hope it doesn't happen, but if it does, it's fine. Just report it to me and we'll get it cleaned up. No horseplay, no goofing around. Computers are expensive, and we don't need to damage any of the equipment here. Personal protective equipment. You don't need to bring anything. You don't need to bring any safety goggles or anything like that. So you don't have to worry about any of that. Base and emergency response procedures. We have the first aid kit here in the corner here, so if you've got an injury or something like that, come talk to me and we'll get you patched up, hopefully, or call an ambulance. Let's see here. Emergency eye wash station, there is none. There's no chemicals, so we don't have any eye wash station in here. Fire extinguisher is located there by the door. We're going to use the pass system, which is, pull the pin out, aim at the base of the fire, squeeze the handle, and sweep from side to side. Hopefully no fires in here, but we have the preparations to take care of it in the event of an accident. So yeah, and in case of an accident, just notify me immediately, and we'll go through and we're going to fill out this accident report together. Hazards unique to the laboratory. I guess the only hazard really is the telescopes. On the day, you really can't look at the sun with a telescope. I know it's obvious, but I remember when I was a kid, long car rides, I used to stare at the sun, and now I got to wear glasses. So let's not do it with telescopes. So that's about it for the safety guidelines. Just going to need a signature and the date.
Do we initial on each of the lines?
No, you just put a signature on the bottom. That's all. My name's up there on the board as far as training provided by me. Title of the class is Astro 154L, date of training, and the department, you can put astronomy and physics. And when you finish that, just pass them down, and they'll be on the end, and I'll come by and pick them up in a bit.
Could you repeat the department?
The department is the Department of Physics and Astronomy, or Astronomy and Physics. everyone's finished with that, let's go ahead and get taking a look at the first lab here. So this is all about the scale of the universe, and really this lab is about dimensional analysis, at least for the first problem. I'll give an example real quick. See, the first problem says, how long does it take for the light of the sun to reach the Earth? And actually, there's a bit of a typo there. Under the hint, it should be time is equal to distance over velocity, not time is equal to distance over time. And there's also, if you look at your second sheet with all the pictures, the picture in the top left, right, that looks like the Milky Way, because it should say D galaxy. Galaxy. I put, yeah, it should say D galaxy.
Instead of the solar system.
Yes, instead of E solar system. Okay. Well, okay. So a quick question: how many of you have seen scientific notation? Okay. Okay. All right. Well, I'll go over it just in case. So we know that the speed of light is 3 times 10 to the 8 meters per second. Now that's going to be our scientific notation. But that's really, if you take your 3 as a decimal point there, and you put a bunch of trailing zeros behind it, this 8 is going to be however many times you move your decimal point over to get it to be the number that you want. 1, 2, 5, 6, 7, 8. So that would be the number, like expanded out. All right, so that's the speed of light, again, is 3 times 10 to the 8 meters per second. And the first question was find how long it takes for the light from the sun to reach Earth. So instead of doing that, as a little example, I'll do how long it takes for light to reach Mars, light of our sun to reach Mars. So the first thing you'll need is the speed of light, and you're also going to need the distance from the sun to Mars, which is 227.94 times 10 to the 6 kilometers. That is the, yes. I'm sorry. I'm talking about the distance from, this is an example problem. For number 1, you all have to do that on your own. As an example, I'm showing the same problem, but instead of from the sun to Earth, it's going to be from the sun to Mars. So it won't be the answer to the first question, but using this example, you should be able to get the answer to the first question. So it's that is the distance from the sun to Mars, and we know the speed of light. That's how long it's going to do. We have to determine how long it's going to take for that light to reach us. So we have our formula here: time is equal to distance over velocity. Velocity being our speed of light. And distance being sun to Mars. So you just plug it in, right? Take our distance here, 227.94 times 10 to the 6 kilometers. Divide that by our speed of light, which is going to be 3 times 10 to the 5 kilometers per second. That's converting from our meters per second here to kilometers per second, knocking out 3 zeros, right? There's 1,000 kilometers in 1 meter, so that's the speed of light in kilometers per second. It's probably easier to use because most things are either in miles or kilometers. So you just plunge that into your computer, a calculator if you've got one, and it'll give you the time in seconds, which happens to be 759.8 seconds. We want to put that into maybe minutes, so we know that there is. We want to convert that to minutes. We know that there is 60 seconds in 1 minute, so just divide that by 60, divide that seconds by 60, and you should get about 12.66 minutes. And so this is the time it takes for the sunlight from our star to reach Mars. You'll have to do this calculation for number 1. Just filling in the different numbers. This is going to stay constant. This is the speed of light, but the distance from the sun to Earth is going to be here. And just fill that in and crunch the numbers, and you should get the distance from the sun, the time it takes for the sunlight from the sun to reach Earth. So that's how you're going to go about number 1. Number 2, you have to order the sequence of pictures. On the other side, you have the other handout. You have those pictures there that are lettered. You got to order them from smallest to largest. So start off with the smallest object on that list and end it with the biggest objects. Put them in order. You can use Google if you need to figure things out. Yes. And then here we go. The closest star is Alpha Centauri. That's the closest star to our planet Earth. You can go ahead and Google that one as well. Yeah, you use the internet as much as you need, but I need calculations for number 1. And other than that, that is the lab. Okay, so and the other assignment that I want you all to do for the white paper that I handed out as well, I want you to anonymously just write, what do you think about space? Like, when you look up at the night sky, how does it make you feel, or what do you think? What are your thoughts and opinions about the universe? You can put as much as a paragraph, a page, or a sentence, or a couple words. Just do it anonymous, and you can turn that one in on the side there on that page when you leave. Just flip it over there. If more than half the class you don't have to turn it if you don't want. And if more than half the class turns in the paper, I'll give everyone extra credit. So just let me know what you think. And then when you've finished your main lab, bring that to me. I'll sign it, and you will be free to go. Are there any questions about the lab? Anything? Concerns? All right. Well, good luck. And feel free to ask me if you have any questions.
How large would a planetary nebula be?
Oh, yes. Planetary, that's a good question. So planetary nebula are actually quite large. They can span anywhere from a couple of light years across. They're quite large. They're the planetary nebula that is going to result from our sun exploding this in the future is going to encompass the entire solar system, and it's quite large. A couple of light years across, I'd say. Okay. Good question.
When I'm looking at somebody, where would I put a planetary nebula?
Right, no doubt. If there are any safety guidelines floating around, just bring them to me when you finish it. I went around and collected them. Yeah, it's a good idea to get to know each other. So for the last question on the lab, it says which unit to put. I just want the unit, like just we have meters, kilometers. I just want the unit that describes the distance between the sun and the earth. You don't have to put like any numbers. Yeah.
It's about 149.6 mil. But I use 149.6 at least that's. I just had a. Were you in the show? Yeah, our professor plugged in the distance between the sun. Using the parameter. So I think he's probably fine. You want it to be in kilometers since this is like it is.
That's the order of
Conversion. And then it's also easier to convert the 3 times 10 equation. There's 3 times 10 to the 8. Yes. Who's it? Yeah, 150 million. And it's pretty easy when you actually do that. Because when you show the work, you just get rid of 5 zeros, so you get 1,500. And that would just divide by 60 with the. Oh, so you do like this part first. Well, I simplified it, because then it makes 5 zeros from the legend to the so probably in the could equal to 1,500. Yeah. Well, I mean, you gotta show it.